All right, we're talking about the magnetic field of the sun, the Earth. And you notice it gets pushed out behind the Earth because the sun's magnetic field is pushing it out away, and the solar wind particles are pushing it out away. The particles hit our magnetic field, and they go funnel around, they come back in, and they end up coming to the poles, and that's how we get auroras. Now the magnetic field on the Earth, the magnetic poles, change over time, and it moves around. And so what happens is, I think I have a video here, hold on a second. Magnetic lines. And so you can see here, this shows the north magnetic pole and how it's moving around over time. It changes positions. And it's still migrating, and in times in the past when we start looking at many hundreds of millions of stuff years ago, the whole magnetic field of the Earth can flip. And the south becomes the north, and the north becomes the south. Just like we see in the sun, it just takes many years. It's a slow process on the Earth. And even now, some people are thinking that we may be heading into reversal, but nobody really knows for sure. All right. And we already talked about auroras, and the auroras are caused by the particles from the sun being funneled down, modified by the magnetic field. They hit the atmosphere, they excite the atmosphere, they glow just like the emission tubes that I showed you when we were doing spectrums. All right. Now, we want to talk about continental drift. This is one of these things that we don't see on any other terrestrial planet. In fact, we really don't see it on any other planets. There's some moons that may have a similar thing with ice plates moving around. But mostly this is very unique to the Earth. But to do that, let's talk about the interior of the Earth. So what we think the interior of the Earth like, and we got a pretty good idea, is we have what we call the inner core. This is mostly iron, nickel, the really heavy materials, and that's probably solid inner core, just because of the tremendous pressure and everything. Around it we have an outer core. This is a liquid outer core, which is spinning around magma and molten rock. That is probably what's creating the magnetic field of the Earth, is in this spinning core right here. Then we have this huge area we call the mantle. And then on top of that, we have the crust. But the crust is not solid. We have these chunks, what we call plates. Continental plates and oceanic plates, essentially just chunks of crust. And what makes them move around, we feel, is they have all this heat in the interior of the Earth. It's still hot from when it formed. When it was liquid, it's still liquid in there. And that heat gets out, but the heat gets out by using convection. And so this hot gas will rise up, and then it'll fall back down again. And it makes these convective loops. And so the hot gas is moving around through the mantle as it comes up. Now notice that if it's making a loop like this, it's going to push this one this way and this one this way, because the loop is going to go that way, and there. And it'll make those continental plates actually separate. So over time, all this convective material moving up and down can start to move the plates around. All right? And that creates continental drift. All right. Now, continental drift was a theory way back in the early 1900s, but didn't really gain any momentum until the 1960s. This is a map of the Earth showing dots. Every one of these dots is an earthquake. So they mapped all the earthquakes on the Earth, and they said, look, the earthquakes all fall on these lines. Not all, but almost all fall on these lines. These lines are the intersection between these continental plates. And so as the continental plates shift and move, that's where most of the earthquakes occur. You also get many earthquakes occurring in mountainous regions. Here's the Rockies. This is all mountains in the middle of Alaska up here. This is the Himalayan plateau or the Tibetan plateau over here. All kinds of mountains. So you do get a lot of earthquakes around mountains as well. And then along any of these plate boundaries. Okay? So if the continental plates, so if the plates have drifted over time, then in the past the continents weren't in the same position they were now. And so we can run backwards. So we're going to run back in time to forward. We're going to run back to a time when there was a supercontinent named Pangaea. So let me see if I can make this work here. There it is. So we're going to go back about 250 million years ago. All right. And you got to remember what was happening on the Earth 250 million years ago. Well, 250 million years ago, the Earth was populated by dinosaurs. Time for, if you take another class, I talk more about that. But there's been 5 major extinction events on the Earth where 70 to 90% of all species on the Earth were wiped out. Well, there was one around 250, 280 million years ago that wiped out 90% of all the species on the Earth. It was the greatest extinction event that occurred. But when that did that, that left a niche open, and that's when the dinosaurs took over. And the dinosaurs reigned from 250 to about 600 or 65 million years ago when they got wiped out. Okay? And then that left a niche for the mammals, and we currently live in the age of mammals. Okay? So it depends on what gets wiped out, leaves the room open for something else to take over. But you got to remember, the dinosaurs were extremely well adapted, and we find dinosaur bones on every single continent on the Earth. Why? Because 250 million years ago, all the continents were together in this supercontinent called Pangaea. So they could walk around to each other. Where nowadays, you find in Australia, you find like different mammals, you find things like koalas and weird animals because they were separated by oceans, so they couldn't interact with other ones, and kangaroos, stuff you don't find in other places. Oops. If I hit the right button here. All right, we're going to play it. And you'll see, this is just running time forward, so that's 220, 200 million years ago. What you see is North America, South America, Africa, India, Australia, Antarctica here. This is Asia loosely put together up here. Okay? And now, over time, it starts to split. You see the split right here. This is called a rift zone. It starts to split. The water comes in. It starts to split here. Okay? And they start to separate. And as they move around, keep watching, eventually you're going to see South America and Africa split. This is one of the proofs for continental drift being accurate, is because the rock structure lines up perfectly between South America and Africa, even though now they're 1,000 miles apart. Notice that North America and South America were not connected. That only has come recently, being recently in the last 25 million years. Watch India. Remember, India started out down here. India, this is India's subcontinent, came up here. It got a whole lot of speed. We're not sure. A whole lot of speed. Came flying up here, and it's going to smash into Asia. Okay? And when it pushes into Asia right here, it's going to push all this here. Well, where does that land go? Well, it has to push it up. This creates the Tibetan Plateau and the Himalayas and the highest mountains in the world right there. Okay? And then we shift to pretty much close to the last 20 million years. These come together right here. So we actually have a land bridge all the way from North America to South America. Australia keeps moving up to here. And this is our current position. And we can project it into the future, but I'm not going to worry about that right now. What we see now is this rift, which is in the middle of the Atlantic, is still splitting. So North and South America are getting further away from Asia, and the Pacific is getting smaller on the backside. All right, so go back to here. Oops. when this occurs, this creates all kinds of effects on the Earth. And it means that our surface is continuously changing as it gets run into, or you run two plates together. You can push them up and make mountain ranges, which is what happens over here. I mean, this was the most obvious one to create the Himalayan range over here. But it also creates other ranges. In here, the Andes get pushed up from this one. And different ones happen at a different time. The Appalachian Mountains, you see, are way over here. Well, that occurred last time we ran into it like 400 million years ago. So they're a very old mountain range, as opposed to the Rockies on the other side. This is a Google Earth picture showing India. And you see India's here, and you can kind of see it, but right here, right in this region here, this is what's called the Tibetan Plateau. And all of a sudden, India ran into Asia, and it pushed up these mountains that are a whole range of 25,000 foot mountains, and the highest peak there, Mount Everest, is 29,000 feet. So this whole region here is extremely high altitude, and it got created when the Indian continent ran into Asia. In fact, if we measure right now, the Indian continent is still moving north. Meaning, it ran into Asia, but it hasn't stopped yet. It's still trying to push up this mountain range. It had so much momentum going into there. Now, we don't think it's making the mountains any higher because the weather and wind is trying to erode them away, and it's probably eroding them away faster than it's pushing them up.